Hello everyone, my name is Hammad Jisr. I'm a doctoral student at EPFL working under the supervision of Professor Dimitrios Lignos, and I would like to present my paper titled Hysteretic Behaviour of Shear Stud Connectors in Composite Steel Moment Resisting Frames. I would like to note that this project is sponsored by the Swiss National Science Foundation. I'll start by explaining the motivation of my work. Steel moment resisting frames are widely used as a lateral load supporting load resisting system in buildings. Oftentimes, a composite floor slab is connected to the steel beams through headed shear stud connectors. As you can see in this figure, the slab transmits seismic loads to the steel beams through shear connection as well as through bearing of the slab at the column face. Shear studs play a vital role in composite steel MRFs, and failure of the shear studs implies a loss of composite action and a loss of the mechanism that transfers the force, the seismic forces from the slab. For this reason, seismic provisions, both American and Eurocode, recommend a 25% reduction in the design shear capacity of headed shear studs as a precaution against severe degradation under cyclic loading. Now, where did the 25% come from? The 25% recommended reduction in the capacity of the shear studs was put in place based on several cyclic push-out tests. For example, here I show two nominally identical specimens that were tested, one using under monotonic loading and another one under cyclic loading. These specimens were tested at the structural steel laboratory at EPFL. Now, from the monotonic curve, you can see that the shear studs are ductile according to Eurocode 4. However, under cyclic loading, the shear studs experienced severe shear strength degradation and eventually failed through fracture of the weld collar as shown in the figure on the right. Nevertheless, these cyclic tests, these push-out tests, these impose large cumulative slip demands on the shear studs, and these demands are not representative of the actual demands under an earthquake load. Another thing that is important to note is that these conventional push-out tests, they do not account for the stress state in the slab, that is tension or compression, nor do they account for the redistribution of the forces between the shear studs of a composite steel beam. So the objective of this work involved the development of a high-fidelity continuous finite element model to evaluate the demand on headed shear studs in partially composite steel beams, both shallow and deep. The hysteretic behavior of the shear studs is compared in subsystems and subassembly, as will be explained later. And the findings are then used to assess the 25% reduction in the shear capacity of the studs as recommended by design codes. Now, it's important to stress that the continuum finite element modeling that was conducted on deep and shallow partially composite steel beams. The degree of composite action was only 30%. So here I show the details of the continuum finite element model that was developed in Abacus. This is a subassembly specimen, a cruciform subassembly specimen. Both shell elements as well as solid elements in the regions of contact were employed. The slab restrained on the top flange of the beam that is typical in composite beams is modeled through hard contact, and the shear studs are modeled through nonlinear zero-length elements that were implemented as VUEL subroutines in Abacus. So here I show the nonlinear behavior of the shear studs. These are characterized by a degrading pinched hysteretic behavior. The modified Ibarra-Medina-Cravinkler model is implemented, and the parameters are obtained through calibration with test data. Now, you can see from this shear stud versus slip behavior that the behavior is asymmetric. And this is because these tests in particular, they account for the stress state in the slab, unlike the conventional test that I had shown earlier. For example, if you look at this figure on the right, under sagging bending, the slab is in compression and Q is positive. Under hogging bending, the slab is in tension and Q is negative. And this explains the asymmetric behavior And this behavior is more realistic, and therefore it was used to model the shear studs in composite beams. Details of the model specifics can be found in the paper below. So the continuum finite element model was then validated with a cruciform subassembly specimen with 30% degree of composite action. The figure here shows that the model predicts the flexure strength and flexure strength degradation fairly well. The margin of error is within 10%. So having established confidence in the continuum finite element model, a parametric study is conducted. Now, the study consists of two beams, a deep beam, which is equivalent to an HA 900 in Europe, and a shallow beam with an European equivalent of IPE 400. Both beams are sized with a degree of composite action of 30%, and the columns are sized to ensure that the strong column weak beam ratio is satisfied and that the column web panel zone is code compliant. Two different configurations were implemented. The first configuration is the cruciform subassembly, similar to the one I had shown earlier. The second one is a subsystem with two bays, and this configuration accounts for the effects of the continuity of the slab as well as the framing action. For both of these configurations, an AISC symmetric cyclic loading protocol is applied up to 6% story drift ratio. Here I present the results of the specimen with a deep beam, that is the HEA 900. On the left is the behavior of the shear stud nearest to the column face. We can see that the shear studs in the subassembly failed at around 4%, as shown here. In the subsystem, on the other hand, the shear stud dropped by 30% at 4% SDR. In both cases, at 2% SDR, no degradation in the shear strength was observed, and the slip demands were within 6 millimeters. The figure on the right shows that the composite beam flexure strength versus beam chord rotation. We can see that the flexure strength in the sub-assembly of the beam in the sub-assembly degraded by 40% due to local buckling in the steel beam. Now this affects, as I will show later, the demand on the shear studs. So how does it affect? So in a sub-assembly specimen, when you have local buckling, due to the absence of restraint and the full framing action in a two-bay system, the composite beams, the steel beams, tend to shorten as the local buckling accumulates. Now this behavior is not as pronounced in subsystems as shown in the figure here. You can see that in a sub-assembly, the amount of axial shortening is much larger than that in a subsystem. Here, the axial shortening reached 50 millimeters, while in the subsystem, it reached around 8 millimeters. Now, this affects the demand on the shear stud in that when you have axial shortening, the slab is pried away from the beam. And this creates additional slip demand on the shear stud, particularly under sagging bending. And this demand can be up to 3 times higher. Now here I show the results for the shallow composite steel beams, IPE 400, for both the subassembly and subsystem. So the slip demands were within 2%, within 2 millimeter for 2% SDR associated with design basis earthquake. In both the subassemblies and subsystem, the slip demand did not exceed 4 millimeter, even at 4% SDR. Here I present the response envelope for the deep composite steel beams, which, again, I stress, these beams have a 30% degree of composite action. We can see that, first of all, the demand near the column face is higher. Near the column face is higher than that away from the column. We can see that demand near the column face is lower than that away from the column face, and this is because of the restraint of the slab near the beam to column joint. So shear studs furthest away from the column experience 50% reduction of strength at 2% SDR, while those closer to the column experience less reduction in strength at 2% SDR. Additionally, the slip demand of these studs exceeded 6 millimeters. We can also see that at 6% SDR, all of the shear studs lost their load carrying capacity. Now, on the other hand, for shallow composite steel beams with the same degree of composite action, which is 30%, the slip demands are less than 4 mm at 4% SDR, and no strength degradation is observed for all studs. So at 6% SDR, we had some strength degradation in the studs further away from the column face. However, no loss of shear load carrying capacity occurred in any of the studs away from the column face. So we can see that the slip demands in shallow partially composite beams are less than 4 mm. So based on these results, I present my conclusions. First of all, for partially composite beams that were studied with a degree of composite action of 30%, the finite element model that was developed and validated shows that in shallow composite steel beams, shear studs maintain their integrity even up to 4% SDR, story drift ratio. Second, unlike in subsystems, in subassemblies, beam axial shortening that occurs due to the accumulation of local buckling imposes up to 3 times higher slip demand on the shear studs. Third, the slip restraint near the beam to column joints leads up to 40% lower slip demands on the shear studs than near the column face, than away from the column face. And finally, these findings show that the 25% reduction in the shear capacity of studs recommended by seismic design provisions may be waived. Thank you very much for your attention, and I would be glad to answer your questions. Here's my email below. Thank you.